Hello my dear wonderful genius students, I'm back again with a new video. This is lecture number 20 on complex analysis and it is the continuation of the last video. Students, in my last video I was explaining the theoretical part of radius of convergence and region of convergence. In this video I am going to solve some numerical problems for finding radius of convergence and region of convergence. So without wasting time, let's get started. Problem number 1. Find the radius of convergence and region of convergence for the following power series. F of z is equal to summation n goes from 0 to infinity z to the power n divided by n factorial. Here we have seen that this power series is expanded about the origin because here z not equal to 0. Now let us find the nth term and n plus 1th term for this power series. So here a n is equal to 1 by n factorial and a n plus 1 is equal to 1 by n plus 1 factorial. So therefore radius of convergence R is given by limit n tends to infinity modulus of a n divided by a n plus 1. Now let us substitute the values of a n and a n plus 1 here. So after substituting we will get limit n tends to infinity 1 by n factorial into n plus 1 factorial divided by 1. So therefore R is equal to limit n tends to infinity 1 by n factorial into n plus 1 into n factorial. Here n factorial and n factorial will be cancelled out. So finally we will get limit n tends to infinity n plus 1. If we put the limit here, then we will get infinity plus 1 whose value is infinity. So we have seen that for this power series the radius of convergence is infinity and the region of convergence is given by modulus of z minus z naught. So here z naught equal to 0 less than r, here r equal to infinity. So the region of convergence is modulus of z minus 0 less than infinity. So this is our region of convergence, z minus 0 less than infinity, and in this region at all points the function f of z will be analytic. Okay. Now let us solve the second problem. According to this problem, f of z is equal to summation n goes from 0 to infinity z to the power n divided by 2 to the power n plus 3. Again we have seen that this power series is also expanded about the origin because here z not equal to 0. Now let us find out the nth term and n plus 1th term of this power series. So here nth term, that means a n is equal to 1 by 2 to the power n plus 3 and a n plus 1 will be equal to 1 by 2 to the power n plus 1 plus 3. So therefore the radius of convergence R will be equal to limit n tends to infinity modulus of a n divided by a n plus 1. Now let us substitute the values of a n and a n plus 1 here. So finally we will get limit n tends to infinity 2 to the power n plus 1 plus 3 divided by 2 to the power n plus 3. Now let us take 2 to the power n as common from numerator and denominator. So finally we will get R is equal to limit n tends to infinity 2 to the power n into 2 plus 3 divided by 2 to the power n divided by 2 to the power n into 1 plus 3 divided by 2 to the power n. Now, let us cancel out 2 to the power n and 2 to the power n. So, finally, we will get limit n tends to infinity 2 plus 3 divided by 2 to the power n divided by 1 plus 3 divided by 2 to the power n. Now, let us substitute the limits. So, after putting the limits, we will get 2 plus 0 divided by 1 plus 0, which is 2. So, we have seen that the radius of convergence for this power series is equal to 2. So, therefore, radius of convergence of this power series is 2, and the region of convergence will be modulus of z minus z naught. So, here z naught equal to 0 because this power series is expanded about the origin less than r. So, in our case r equal to 2. So, this is the region of convergence. Now, let us draw the circle. The radius of the circle is 2 and the center of the circle is 0, and the region of convergence is given by modulus of z minus 0 less than 2. That means, within this region this function f of z will be analytic at all points. Next, let us move to problem number 3. According to problem number 3, f of z is equal to summation n goes from 0 to infinity z to the power n into n factorial divided by n to the power n. Again, we have seen that this power series is expanded about the origin because z not equal to 0. Now, let us find out the nth term and n plus 1th term of this power series. So, here nth term, that means a n is equal to n factorial divided by n to the power n, and a n plus 1 is equal to n plus 1 factorial divided by n plus 1 whole to the power n plus 1. Now, let us apply the formula for finding the radius of convergence, which is r is equal to limit n tends to infinity a n divided by a n plus 1 modulus. Now, let us substitute the values of a n and a n plus 1 here. Limit n tends to infinity n factorial divided by n to the power n into n plus 1 whole to the power n plus 1 divided by n plus 1 factorial. Now, let us simplify this term. So, we will get r is equal to limit n tends to infinity n factorial divided by n to the power n into this term can be written as n plus 1 into n plus 1 whole to the power n, and this term can be written as n plus 1 into n factorial. Now, let us cancel out the terms, this one and this one, this one and this one. So, finally, we will get limit n tends to infinity n plus 1 whole to the power n divided by n to the power n. Now let us take common n from this term. So finally we will get limit n tends to infinity n to the power n into 1 plus 1 by n whole to the power n divided by n to the power n. So finally we will get limit n tends to infinity 1 plus 1 by n into whole to the power we know n. The value of this limit is e. So we have seen that the radius of convergence of this power series is e. So radius of convergence of the power series is e, and the region of convergence is given by modulus of z minus z naught. Here z naught equal to 0 less than r, which is e. Now let us draw the circle. The radius of the circle is e and the center of the circle is 0, and the region of convergence is given by z minus 0 less than. Now let us learn how to find out the radius of convergence and region of convergence by using singular point method. Problem: find the radius of convergence and region of convergence of the function this one if this function f of z is expanded about the origin, that means about z equal to 0. Second, if this function f of z is expanded about z equal to half. Third problem, if this function f of z is expanded about z equal to minus 2. Now let us solve. Given f of z is equal to 1 by z minus 1 into z minus 2 into z plus 3. Now let us find out the singular points. Students, we know that singular points are the points at which the function f of z is not analytic. So here we have seen that if we put z equal to 1 or z equal to 2 or z equal to minus 3, then this function becomes infinite. So therefore the singular points for this function f of z will be z equal to 1, z equal to 2 and z equal to minus 3. So here z equal to 1, 2 and minus 3 are the singular points. Next, let us solve problem number 1. So problem number 1 says we have to find out the radius of convergence and region of convergence if we expand this function f of z about the origin. Now let us find out the location of the singular points on the eigenplane. So here this is the location of the first singular point, and this is the location of the second singular point, and this is the location of the third singular point. Next let us draw a largest possible circle about the origin or about z equal to 0 such that within that circle this function f of z is analytic at all points. If we draw, then we will get this type of circle where the radius of the circle is 1, r equal to 1, and the center of the circle is 0. So therefore the radius of convergence r equal to 1 and the region of convergence will be modulus of z minus z naught. Here z naught equal to 0 less than r, whose value is 1. Next let us find out the radius of convergence and region of convergence if we expand f of z about z equal to half. So if we draw the largest possible circle about z equal to half, then we will get the radius of the circle as half. So in this case the radius of convergence is half, and the region of convergence is given by z minus z naught. So in our case, z naught equal to half. Modulus of z minus z naught less than r, which is half. So this is the solution of question number 2. Next, question number 3. If we expand f of z about z equal to minus 2, then we will get the radius of the circle as r equal to 1. So in this case, the radius of convergence will be 1, and the region of convergence will be modulus of z minus z naught. So here z naught equal to minus 2. So minus z naught means z plus 2 less than r. So in our case, r equal to 1. So for question number 3, the radius of convergence is 1 and the region of convergence is modulus of z plus 2 less than 1. This is all about today's video, and I hope that after watching this video, you can find out the radius of convergence and region of convergence by using formula and by using singular point method.